Hey guys, sorry for not being able to be in class today, but I figured this will serve two purposes. Item number one, I get to take my kid to her doctor's appointment, but also this will be available to you for you to use in whatever capacity you might need to use it to be successful on our exam. As obviously that's going to be where this information is going to come back to, right? We just took the Unit 2 test, and a decent number of folks are realizing, okay, the notes, the labs, all of these things are going to come back together and be found again on the exams. So I wanted to give you another mode, another medium with which you can get this information. In the book I used to teach from, this was chapter 2. I should probably edit that at some point, but we're entering unit 3, which is all about matter and how matter changes. So for our third unit, we have to go back to, and I know we already defined this last unit, but we have to go back to defining what that matter was. So matter is going to be anything that takes up space and has mass. We use this seemingly vague definition as a way to differentiate matter from things like energy, right? Energy could be light, it could be heat, it could be waves, any of those sorts of things. So matter is this physical, tangible stuff. And it's made up of two components. How much is there, being mass, which we just got done talking about, and volume. Again, this was all part of our density unit, right? How we described that matter. One of the ways we did it was density, and we spent the last unit going over how we can differentiate densities, how we plot densities, use them to identify various substances, things like that. So this is all going to come back in several big ways. We might not do density calculations themselves, but we still have to talk about this matter and how it can change. So instead of talking about it in quantitative measurements, now we're moving towards using these qualitative measurements. So adjectives that we might use to describe matter would be physical properties. And that's going to be the first one we're going to have here, right? It's going to be something that we can measure or observe without changing what is present. So you can tear a sheet of paper in half, but it's still a sheet of paper. You can, crumble up a sheet of aluminum foil, but it is still aluminum foil. So some examples of physical properties would be things like color, or hardness is actually a scale that is used in geology to describe more or less roughly the same idea of density of like different kinds of minerals. So chalk, you take a piece of chalk like sidewalk chalk and snap it in half, you still have chalk, but it is nowhere near as hard as a diamond would be, right? You're not going to just break a diamond in half with your bare hands. The MP and BP on this particular slide represent melting point and boiling point. You can melt something or cause something to boil and then bring it back the other way, right? We can melt ice cream and then refreeze the ice cream. So those sorts of physical changes can occur, and they're not going to change what is present. We're going to get into that in a lot more detail here in a little bit. Chemical properties are going to be things that can only be observed once you change the composition of what is present. So a chemical property would be like a piece of lumber's ability to burn, right? Once you burn that lumber, it is now no longer, it's no longer a log of wood. It is now soot, ash, smoke, whatever it was turned into. Decomposition is another great one for chemical changes. Things eventually just decay, fall apart. Fermentation, sure, you could use this for adult beverages, but it's also the same anaerobic process that occurs inside humans producing lactic acid, the stuff that makes you sore after an intense workout. Or just the mere fact that things react together. I can put chocolate syrup in my milk and they don't react together, right? I have to physically stir them and mix them in order to get them into a solution that we would call chocolate milk. And then if I let it sit long enough, it will eventually settle back out. That's an example of physical properties. It's not chemically reacting. The milk and the chocolate milk aren't chemically reacting together. Typically, your chemical reactions are going to be things that are not capable of going backwards, right? You can't get back what you had. The next set of the notes, just some definitions we got to get out of the way so that we can start having these conversations, are going to be the different kinds of matter that we have available to us, right? So we know the different states. The three primary ones, I hope, are things that we already have a good understanding of. Even if it is, if we don't have a good understanding of the fourth one yet, we'll talk about it briefly. It's way more a topic for like astronomy, but we all know solids. Solids are going to be like the desk that you might be sitting at, the chair you're sitting on, the cell phone in your hand, things like that. Liquids, this will be like the water in your water bottle, right? They have a definite volume. You can measure what that volume is, but it's going to take the shape of whatever container you put it in. I could have 5 milliliters, on the floor versus 5 milliliters in a graduated cylinder. Different shapes, but still 5 milliliters. Gases are going to be things that do not have definite volumes or definite shapes. They're easy to move around and flow around. Now we're going to look at particle pictures here in a little bit of these various substances, and that's really where you're going to get the idea of why they might have these definite shapes or definite volumes. And of course, we're going to circle back to all of this later in the year when we talk about intermolecular forces and the things that hold those molecules together, making them solids versus liquids, or a lack thereof, allowing them to be gases. Now, this is not the fourth state of matter. But another term we might use with gases, a synonym, if you will, is going to be a vapor, right? It doesn't sound right in everyday vernacular, everyday vocab, everyday language to describe this as water gas, right? It's water vapor. It is steam. We haven't chemically changed it, right? Whether it's frozen, a liquid, or in a gas phase as steam, water is water. It is H2O. Might call it ice if it's a solid, but it is still frozen water. It's H2O. When it's a liquid, it is H2O. When it is a steam, when it becomes a gas, a vapor, it is still H2O. We haven't separated the hydrogen from the oxygen. It's just in a different phase. It's got literally more or less energy. That's how we're going to relate all of this here in a little bit. So again, vapor was not the fourth state of matter. Please don't write it in that blank in assignment number 1. This is a synonym for our gases. We'll use the two interchangeably. The data table that you have in your packet as well in assignment number 1. This is just a nice little way to break down what's going to happen. We're going to come back to these a lot over the next couple of days. As we progress throughout the unit, there's a lot of good conversations we can have here, but it's nice to be able to have this quick cheat sheet, this quick reference to come back to. So in terms of volumes, can we measure a definite volume for a solid? Absolutely. 9 times out of 10, it could be length, width, and height. Maybe it's a triangle. You do 1/2 the base times the height, things like that, right? We can measure those volumes, measure those areas, whatever it might be. Liquids are also going to have a definite volume. We can measure them in a graduated cylinder, in a beaker. We can store them and mix them in an Erlenmeyer flask, all those things that we've talked about in the first part of the year. Gases, however, no, gases expand to fill the shape of their container. Whatever that volume of the container is, the gas will occupy that. And again, particle pictures to come to kind of give you a visual for it all. We just want to make sure there's a spot where you've got this written down somewhere. Shapes, solids, obviously they're going to have a definite shape. The moment the shape of a solid becomes in question is usually when those forces holding it together as a solid begin to fall apart, or there's too much energy and they become a liquid, right? Liquid will take on the shape of whatever container it is that they have around them. So liquids have a definite volume, but the shape will be whatever container it's sitting in. Gases do not have a definite volume nor a definite shape. There's no strong intermolecular forces holding those together at all. Sorry for the punctuation here. I think I need to go in and make a space between the temperature and increase. But what is the result of a temperature increase, right? What's going to happen if we increase the temperature? Maybe you've noticed this in the summertime when it gets really hot, it gets really humid. If you guys live in an older home, you might have issues where doors might start sticking and they become difficult to open or difficult to close. That is because there is a small expansion as things heat up, right? We talked about the Kelvin scale having absolute zero at the very bottom. It is the coldest temperature possible. It is when, in theory, all motion should stop. Things get slower the colder they get. So in this case, it's literally the exact opposite. The more you heat something up, the more it might move, the more it might expand, the quicker those particles might be moving. Now, if it's still a solid, you're not going to notice too much of an expansion, but it is possible, right? Even my own hands, right? If I'm wearing, a ring on my hand or the watch on my arm, as temperatures increase, if I'm working out or if it's just a really hot, humid day, you'll notice that your hands will swell. Literally, right? It's the same idea. Solids and liquids will do the exact same. Gases have a dramatic expansion. You heat up a balloon, it will expand and expand and expand until the structure of the balloon itself can't hold that volume anymore, and it ruptures and pops or explodes, whatever you want to describe it as. But they have a very, very large expansion as a result of a temperature increase. Conversely, they have a very large contraction, right? They get significantly smaller the colder it becomes. Same with compression, right? Solids do not compress easily. Liquids do not compress easily. In fact, we take advantage of this in terms of hydraulics. Gases do compress really easily. We've all seen that one kid at a party, try to sit on a balloon to pop it, and instead it just gets smaller and takes on a different shape, and it doesn't actually pop. You can compress gases. So we wanted to make sure you guys had a quick little cheat sheet for all the different things that these guys can do. We're going to come back to a lot of them as the unit goes on. To give you your first particle picture, that's on the next slide, but this also introduces, let's go back to that fourth state of matter, plasma. Plasma is formed only at really, 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 really high temperatures. Basically, it's an ionized phase of matter. We'll talk about what it means to become an ion later, at least in great detail. Where I'll test you on it would be later. But you kind of get the same sense from literally what I just described with solids, liquids, and gases. The hotter they become, the less ordered and organized they become. The forces that might be holding these little atoms or molecules together become weaker and weaker and weaker, and there are fewer connections molecule to molecule. That's exactly what's happening, right? As we go from a solid, it's this very organized, rigid structure, to a liquid, it is less contained, less organized. To a gas, there's no containment at all. Those particles are bouncing around, moving wherever they want to go. And a plasma, it actually gets so hot that it actually just like loses its outermost electrons. And you get these positively charged particles and negatively charged particles running around colliding with each other. And so that's our state of plasma. But those are the individual ones. We'll have lots more particle pictures in the next several slides, right? We've got a particle picture of a solid. You notice how organized and neat that is. All of those particles are really, 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 really close together, whereas a liquid, there might be a little bit of gaps, right? There's a little bit more space between them. There's room to move around. This is why when you drop in some food coloring, the food coloring spreads out. It takes some time, usually. It depends on a couple of factors, but it will spread itself out as evenly as it can within that solution that you dropped it in. Whereas gases, those particles are bouncing all around. You've literally got to put a stopper at the top of that bottle on the far right in order to contain the gases. Otherwise, they'll just leave, right? They'll peace out, right? You opened the door, they're leaving. It's like you guys at the end of a PEP assembly, right? All scatter. In your notes, you will see a copy of these three beakers, right? We're going to talk about labeling the phase changes between them. First, we got to label what each one is. So the bottom left box, obviously, this is going to be an example of a solid. Notice the gap off to the right inside that beaker that you've got over there. So solids have their own shape. They're not dependent upon the container that they are in for the shape that they'll have. Liquids, again, that's going to be the beaker right there in the middle. Your liquids have a little less order to them. They occupy the space of the container that they're in. They can move around one another, but they don't have enough energy to just kind of peace out and take off flying in the upward direction. They don't have enough energy to do that yet. And then obviously gases do. They do have enough energy in order to do that. And so we had to put a little lid on that one, right, in order to keep those gases contained. But they're just bouncing around in there like looking at people play or do one of those bumper car sort of things, right? That's how I like to envision gases inside the container. It's like a three-dimensional bumper cars. They're just like hitting the walls. They're hitting each other. They're going in different directions. We'll talk about that a lot more when we get to kinetic molecular theory, but that's the idea. And so I just wanted to get you guys used to seeing these particle pictures. Now let's talk about the phase changes between them. We are all familiar with this first one. As you go from a solid into a liquid, we would call this melting, right? You can take ice and turn it into water. You can take frozen ice cream and turn it into whatever like soupy liquid it becomes if it sits out too long, right? We've all seen this happen. Solids can easily turn into liquids. Even butter, right? You put butter on a frying pan, it will, with enough heat, turn into a liquid rather easily. The next phase change, going from a liquid to a gas, we're also familiar with. If you spill your water in the back of Mr. Willis's classroom and you're too nervous, intimidated, whatever, to mention it, which is silly, I got paper towels, just tell me. But if you don't want to mention it for whatever reason, eventually it will evaporate, right? The process of going from a liquid into a gas we call evaporation. Recall the synonym for a gas phase is vapor, right? For the gas phase itself, we don't say water gas, we say water vapor. Evaporate, right? That's my little memory cue for that one. It is the process of gaining enough energy. It usually takes some time, does happen slowly. You can expedite the process, speed the process up by adding some heat, sure. But eventually, they'll eventually enter the gas phase. That'll happen with any of those water molecules that were left out on a desk or on a floor or anything like that. Eventually, it will evaporate. Going back the other way, we can easily cause things to condense back down into a liquid. This is what happens out on a hot, sunny day when you have a glass of ice water and you leave it sitting out and you get that water on the outside of the glass. Why does the outside of the glass get wet? It's not because you're like sloppily sloshing the water around and it spills over the outside, or the water moving through the glass itself. It's not doing any of those things. The condensation on the outside is literally the water that was in the air, in a vapor, in a gas phase that strikes that glass, gets colder, and then loses its ability to maintain its gaseous form, if you want to call it that. Sounds pretentious, but that's really what it is. It loses the ability to remain a gas and goes back into the liquid phase. We call it condensation. It happens all the time. We see it in the mornings right now when I walk out to my car, right? This day and age, it's hot enough in the daytime to where we have a lot of water in the atmosphere. It's very humid these days. And then when it cools down at night, all that water from the air condenses and it creates this, fog on the front of my windshield, right? It's the exact same process. We could also go from a liquid to a solid, which we're all familiar with because all of us have one of these at home. It's a freezer, right? You're going to freeze that solution. You're going to go into that solid phase, right? And this happens at all times. In fact, it's weird to think about, but technically, we could describe anything that is a solid, even at room temperature, we could describe anything that is a solid as frozen. Now, we typically will think of things that are frozen as being below 32 degrees Fahrenheit or 0 degrees Celsius or below 273 Kelvin, but technically anything that's a solid is frozen, right? You just haven't reached its melting point. That's exactly what we have happening here, right? So solids, I don't mean to freak anyone out with the moving particles, but it is important to note that just because something is a solid does not mean those molecules and those atoms are not moving. Everything is in motion at all times. If it is in the form of a solid, it's not moving much, but it is still in the form of but it is still moving. The only time these atoms, these molecules will fully stop moving is at absolute zero. And we talked about it a little bit before, it's that theoretical limit because the mere act of observing something at absolute zero would require a photon, and, the collision of those particles, the photon with, your electrons or your atom of your nucleus or whatever is going to give it a little bit of energy. And now it doesn't have 0 Kelvin energy, 0 Kelvin temperature. It is now moving again. And so, we could get into that whole debate as to why absolute zero is a theoretical limit, but even solids like the desk you're sitting in, the chair you're sitting in, even your bones, those atoms, those molecules are vibrating, oscillating very, very little, right? Not nearly as dramatically as this little simulation shows, but they are moving. Liquids, there's a lot more movement. They are moving a lot quicker, right? So for our example here, we had copper. Let me go back. Copper has a melting point of 1,083 degrees Celsius. So any temperature below 1,083 degrees Celsius, which is insanely hot in the terms of Fahrenheit, it's going to remain a solid, and that's awesome. But how do we stretch it out and reshape it into all these different things? You have to heat it up to its melting point when it becomes a liquid, and then you can change its shape. That's the idea. So copper's liquid phase, those particles have a lot more energy. They're moving a lot more rapidly. They're able to bounce around, move a little bit more independently of one another. And technically, yes, it is possible you can get copper to become a gas. You just have to be at temperatures greater than 2,595 degrees Celsius, which is insane. But you are absolutely capable of getting into the gas phase. And again, it just relates temperature with phases. That is it. Just because something is solid doesn't mean it got 0 energy. It doesn't mean that it's completely frozen in place. Those atoms, those molecules are still always going to be moving as long as we're above absolute zero. So those are physical and chemical properties and the different states that matter can have. Now we're going to talk briefly about physical and chemical changes. Physical changes dictate basically what the object itself will look like. I can take a sheet of paper and tear it in half. I haven't changed it in terms of what it's made up of. It's still made up of, the paper is still made up of all those little sucrose molecules or whatever it is that's inside the trees that we're using. That hasn't changed. We haven't chemically altered the paper. We just now have a smaller sheet of paper. right? We have 2 sheets of paper, but it's still paper. We can take a log of firewood, split it down the middle with an axe. It's still firewood. It's a smaller piece of firewood, but it's still firewood, right? So other examples of physical changes could be boiling or melting, right? You're not changing the chemical composition of those substances. You're just taking it from the liquid phase to the gas phase, or from the gas phase to the liquid phase. You haven't changed what it is. You can physically cut, bend, split, crack, these sorts of things. Even like a beaker in a lab, if it shatters, it's still glass. It's still silicon dioxide. It hasn't changed. It's just in a bunch of small useless pieces that can hurt you. So those are physical changes. Once you boil water, is it still water? Yeah, absolutely. If you put one of those lids on top of a pot of boiling water and you pick the lid up, you'll notice some water rolling down off the top, getting all over the countertop, right? It is still H2O. It hasn't changed its chemical composition. It's not hazardous in any way. It's just, well, maybe aside from its temperature, it's still just water, right? So a lot of these physical changes are capable of being reversible. That's really the one big takeaway, right? If I bend a piece of metal, usually I can bend it right back into shape. Now, if I cut a log of firewood, yeah, I'm probably not going to be able to get that back into a larger log of firewood. But if I boil water, I can collect the vapor that comes off of it and condense it back down into a liquid. In fact, that's one of the things that we're going to talk about for how we can separate some stuff in the world of sciences. And there might be some examples that we'll use later on. Chemical changes, a new form of matter is created. It is chemically different than what you started with. Good examples of this are like the rust that might build up on your car or a building, if it's got like a metal roof or something like that, right? Once it begins to rust, it is now no longer that strong, sturdy steel that your car needed the structural integrity for. It's now this rusted hunk of flaky stuff that falls apart easily, right? I had a really, really, really old car at one point, sat out in a field for years, rained on, the whole 9 yards. It was really sad to see it go. But at one point, this car was brand new, shiny, and beautiful. And you could put your feet in the floorboards and not worry about your foot going through. But it sat in the rain for so long that it rusted, that one day I sat down in it just to see if we were trying to get it going. And my foot went straight through the floorboard. It had rusted through, and the rust did not have the same structural integrity that the steel originally had. Another good example of a chemical change would be to burn something, right? You take that piece of paper that you tore in half and you take both those sheets and you throw it in a fire. You're not getting the paper back. You don't have smaller sheets of paper now. You literally have smoke and you have ash. Like, it is turned into something completely different. Mixtures. We got to talk about mixtures. There's going to be a couple different kinds of mixtures, but mixtures are physical blends of different kinds of substances, right? And we've got 2 vocab terms we can use with describing mixtures. We have heterogeneous mixtures, which are not uniform all the way throughout. So it's like gravel on a driveway, chocolate chip cookie, soil, anything where you might have different sections that have different pieces. You use a blueberry muffin, for example, right? You might take a bite and you get all muffin. You might take another bite. It's all blueberry. It's all mixed together. Right? Versus homogeneous mixtures are going to be the same composition all the way throughout. You mix up your Kool-Aid or your Gatorade solution or your chocolate milk, right? Chocolate milk for a moment would be homogeneous because you stir it up really well, and it's the same all the way throughout. You let it sit for a little while and it begins to settle, and then it would turn into a heterogeneous mixture. It was not uniform all the way throughout, right? You get your milk up top and usually the chocolate syrup down below. The air is a really good example of a homogeneous mixture, right? I'm not going to walk into a different room and suddenly get a full, face full of nitrogen gas, right? The atmosphere that we're breathing right now is mostly nitrogen. It's like 50% nitrogen. That would be bad if we walked into a room where it was all nitrogen, because we need the oxygen that's part of it, right? So we don't really have to worry about, the atmosphere that we're breathing being heterogeneous. That would be bad. You walk into, this little region over here in between these trees, and all of a sudden there's no oxygen. That would not be good. So the air would be a homogeneous mixture, right? We often refer to these homogeneous mixtures as solutions. In the density lab that we just did, that was why I referred to them as solution A, solution B, and solution C. They were the same all the way throughout. They're homogeneous mixtures. Really, all I did was I took food coloring and I put it in water for one of them, and I took another one and I put food coloring inside isopropyl alcohol. Rubbing alcohol, right? That was it. Those are my solutions. It's the same all the way throughout. Every part keeps its own properties. That's another good one, right? Just because we have a mixture of salt and water does not mean the water behaves any differently, right? Water is still water. It's still H2O. It doesn't matter if we dissolve salt in it or not. Solutions are going to be your homogeneous mixtures. They're mixed molecule by molecule, which is why you can never tell the difference between them. You can have homogeneous solutions in any variety of these different states of matter, right? The most common one would be the atmosphere that we're breathing. It would be a gas in a gas. You can have a liquid dissolved in a liquid. That works perfectly. You can even have gases dissolved in liquids, right? The example that I used in class on the 18th was talking about the ACT problems where it was dissolved oxygen concentration inside the water in populations of fish, right? When we were talking about our graph stuff. But literally, that's how fish breathe. That's how aquatic organisms breathe. Is there's oxygen gas, like the same stuff we're breathing, dissolved in the liquid, dissolved in the oceans. You could even have a solid dissolved in a solid. We call those metal alloys, right? If you're a big Marvel fan, Tony Stark's armor was a gold titanium alloy. Literally, you just melt gold, you melt titanium, mix them together, you have yourself an alloy. That is a homogeneous mixture. That was the idea there. We're going to use this term a lot. I was about to say phrase, but phrase and phase sound similar. So we're going to use this term a lot. The term phase is going to describe any part of a sample with that uniform, mixture, if you will. So homogeneous mixtures will be a single phase. There's only one part to it. It's the same all the way throughout. If it's a heterogeneous mixture, you're going to have multiple phases. In this portion of the solution, it has a concentration of, chocolate chips. In this part of it, it's a concentration of just cookie dough, right? And that's what makes your chocolate chip cookie. So there's multiple phases within a heterogeneous mixture. Homogeneous mixtures, single phase all the way throughout. It's uniform the entire way. So we might throw that out there. In some of the example problems that we are going to be using and talking about, we might talk about different ways that we might separate some of these mixtures. One of the easiest way to separate some of these mixtures might be, filtration really is probably going to be one of the best ones. You guys, if you or your folks drink coffee, this is all we're doing, right? We're filtering the coffee beans and the coffee grounds out of our coffee solution. The coffee then becomes the homogeneous solution at the end in a single phase. So filtration is a really good way to separate out a solid from a liquid. You can basically separate them by size. It just depends on how what the rating for your filter paper is, right? You have different filter papers with different ratings, so they let larger or smaller things through. Obviously, it's kind of like the entrance to a doorway, right? The larger the gates, the more people you can let in at one time. If you're filtering something, the idea is that you want that gate to be as small as possible, so only the little things can fit through, right? That's kind of the idea. There's another one called paper chromatography. We'll use this one a lot more in college than we probably will here, but we can use this with inks and dyes and things like that. Basically, what you end up doing is you have a solution that starts at the bottom where that solid line is, and it travels down the paper, and the stuff just separates out into the individual components that it was comprised of. We use that one a lot. Distillation is a really, really good one that we can talk about. This will pop up in some of the examples that we have in class. So if we're separating a mixture by distillation, the idea is we're taking advantage of different boiling points. So if I wanted to separate salt from water, let's say the apocalypse occurs, I'm about to save your life, right? And we're out of fresh water. You need to get some fresh water and you're stranded by an ocean, a body of salt water. You can literally use a trick like this, right? You just get that salt water to begin to boil. And as it boils, the water comes off, and the salt, the sodium chloride or whatever else might be there, is going to stay behind in the container that you had. All you need is some way up top to collect the vapors that come off, and then find a way to condense them down, just cool them down, bring the temperature back, and you can separate out the mixture. You can separate out the water from the salt. Really quick, really easy. In fact, most survival people or people that you might see on survivor shows, survivor style shows, they can literally just put a leaf over the pot of boiling water and have it drain off in a different direction, and that's how you're able to get some liquid water out of it. It works great. So that's distillation. That's all distilling something is. Next, we've obviously got more definitions that we need to talk about. So we're going to talk about how we classify our substances. We are either going to have elements or compounds. You can have mixtures of elements and compounds, mixtures of elements, mixtures of two different kinds of compounds, whatever. But we're really going to break them down into these two categories, right? So elements are going to be the simplest kind of matter that we can have and still retain those properties. We'll talk about subatomic particles later. That's probably going to be the next unit if I look ahead at the calendar. So elements, just like the elements that we find listed on the periodic table, we can't break down an element or an atom of aluminum, any further and have it still have the properties of aluminum, still have it be that shiny metal that is easy to move and bend and things like that. If we broke an atom or a single element, a single atom of aluminum down any further, it's no longer going to have those same properties, right? So these elements are going to be the simplest form of matter that's out there, right? They're all one kind of atom. So if I'm looking at an atom of hydrogen, it's going to have one proton and one electron. That's it. We'll talk about isotopes and stuff later for those of you who might be a step ahead or coming back to review for the finals, right? But the point is, with these elements, every atom of hydrogen is going to be identical, right? It's going to have one proton, one electron. Helium is going to have two protons, four electrons, or two protons, two electrons. Lithium, three protons, three electrons, so on and so forth, right? They're always going to be the same. Compounds are going to be made up of those elements. So we've already talked about water, H2O. We've all known the chemical formula for water for years, right? Probably something you learned before you even knew what those letters meant. It's got two elements, two atoms of hydrogen and one atom of oxygen, right? H2O. It's always going to be found in those groups. If you want to break them down, you can. Once you break H2O into its constituent parts, H and O separately, now they behave differently. Water is required for life, right? It's required for a lot of those biological processes. So is oxygen for the most part. Plants need water. Plants don't need oxygen. That's a byproduct for them. So they behave differently chemically. And hydrogen is like incredibly flammable, right? The Hindenburg was a big deal. So we got to be careful when we separate some of these compounds, right? We break the compounds down into smaller and smaller pieces. They no longer retain the same properties that they had before. Another good example is sodium chloride, right? Sodium chloride is salt. Salt is essential for biological processes. In biology, you talked about sodium and potassium pumps, moving things in and out of cells, all of that fun stuff that happens with neurochemistry and neurotransmitters. It's basically sodium potassium pumps, right? Boiled down, that's what it comes down to. But if you take sodium, pure sodium by itself, it's incredibly explosive when combined with water. If you take chlorine by itself, it's incredibly toxic. It will kill you. But when you combine the two, you get something that is essential for life. It's kind of funny. So that's the difference between compounds and elements, right? Compounds are a mixture, physical connection of those elements together, right? Creating something brand new, a new compound, something that does something different. Plants do this all the time. You learned about this in biology. I was tutoring someone in biology over the summer. You can take carbon dioxide, you can take water, and you can make sugar. Sugar behaves very differently than carbon dioxide and water. And we, as consumers of those sugars from the plants, break that sugar down into carbon dioxide and water, and we use that energy from it. So again, the difference compounds are made up of multiple atoms and multiple atoms of multiple elements. It's not just a physical blend. They are chemically combined with chemical bonds. We'll talk about those in a little bit. But elements are going to be just like if I've got a chunk of aluminum, it's going to be pure aluminum, right? So, good examples, and I like this little T-chart, right? I think this is actually in your notes. Compounds are made of one kind of material. It's what the formula for table salt would be NaCl, right? Sodium chloride. It's made up of sodium chloride. It's a bunch of sodium chloride. Salt water would be a mixture. It's made up of sodium chloride and H2O, right? NaCl and H2O. And so it's a mixture of those two. The sodium chloride is not physically bonded to the H2O. You can separate them the way I just talked about with distillation. Compounds are going to be made by a chemical change, right? You chemically react those things together. Plants take carbon dioxide and water and chemically react them together until they build a sugar molecule. Mixtures, it's just a change in a physical state, right? It could go from a solid to a liquid or a liquid to a gas, any of those. And then compounds are going to have a definite composition. It's always going to be the same all the way throughout. So if I've got a container of Morton's table salt at home, it is sodium chloride, and it's going to have the same composition, top of the container all the way down to the bottom. Mixtures might have variable compositions, right? Chocolate chip cookies aren't the uniform all the way through. They have different regions that have different stuff, things like that. So asking questions, which is it? This first one in class, this one is definitely just going to be what we would describe in terms of particle pictures. This would be just an element, right? This is an element all by itself. Each one of those individual dots is identical. So we could say these are all elements of hydrogen, or these are all elements of oxygen, or carbon, aluminum, sodium, whatever. It doesn't matter. If we want to make them a compound, That's going to look a little bit more like this. In fact, I drew it out this way because it looks a lot like H2O, right? You've got one central oxygen atom, and next to each of them are two hydrogens, and each unique group, each physical set is the exact same, right? So each one of those compounds, there's what, 1, 2, 3, 4, 5, 6, 7, 8, there's 9 compounds of water here, right? 9 molecules of water here. That's the difference between an element and a compound. This guy right here, this would be a mixture of elements, right? None of them are physically bound to each other. They're not touching. This is a mixture of elements. Maybe this is a mixture of hydrogen atoms and a mixture of, I don't know, calcium atoms. I'm just making things up, right? Small versus large. Point is, it's a physical mixture. It's a physical blend. We should be able to separate these. That's the idea. Elements versus compounds. Compounds can be broken down. Sorry, compounds can be broken down into simpler substances, but elements cannot. This is what we refer to as a chemical change. A chemical change is when we produce a new compound. So we are taking sugar, and inside our bodies, we're breaking down that sugar into carbon dioxide and into water, releasing the energy that was held within those chemical bonds. And it has now a new composition, right? It's no longer sugar. It cannot sustain us the way the sugar molecule once did. Once broken down, it's fragments of its former self that are no longer useful, and we breathe out the carbon dioxide. We might breathe out the water as well, or excrete it in other means. You guys know what I mean. But we get rid of it, right? We get rid of the byproducts. We get rid of the waste. We don't need it. Chemical changes can have multiple ways in which they indicate that a chemical change occurs. One of the most common, and we'll talk about this actually in our next set of notes, is heat or light being produced, right? Oftentimes in a chemical change, things might heat up, right? If you have a chemical reaction occurring where things warm up, let's say you needed, I don't know, icy hot. That's a good example. It's a chemical reaction that occurs and it creates that heat, allowing, whatever spot you put the icy hot on to feel some sort of heat and relief from the stress and inflammation. Light's another good one. You crack a glow stick, right? The glow stick doesn't begin glowing until you crack the inner tube. The two compounds mix. They begin reacting together. They produce light, and as long as the chemical reaction is occurring, you're producing that light. The moment the chemical reaction is done and there's no more reactants anymore, it's finished. That's when the glow stick, the light itself begins to dissipate. It's no longer being produced. You can put a glow stick in the freezer to prolong that because you're slowing the molecules down. They react at a slower rate. Well, all those are things that we'll talk about later, but heat and light are often evidence of a chemical change. We'll go through all 5 pieces of evidence for a chemical change later. Let's see, properties of a compound. The elements that make up a compound are going to have, and I've already alluded to this, drastically different properties than the compound they make together. Again, table sugar. Table sugar is sucrose. It is C6H12O6, right? It's got carbon, it's got hydrogen, it's got oxygen. Independently, they all do very different things. But when you combine them together in that format, C6H12O6 from biology last year, you're going to get sugar. And that is something that is essential for all life, right? We need it. It's a good way of storing energy and breaking that energy back down, breaking the compounds back down to release the energy for later on. Another good example is sodium chloride, right? Sodium chloride is just table salt. That is it. Sodium on its own is toxic and incredibly combustible. Chlorine by itself will kill you. But together, they create something that is actually essential for life to exist. Right? We need it for all the sodium and potassium pumps inside our body. Water is another good one, right? Oxygen we need to breathe. Hydrogen is incredibly flammable and explosive. Water, when they combine to make water, they have very, very, very different properties, right? Neither oxygen nor hydrogen by themselves is stable in any capacity, but water, incredibly stable. We have oceans of it, right? So chemical changes result in new compounds that have completely different properties. I like this little flow chart. This is on the notes that it's on Teams. You can talk about the different ways in which we can categorize all the different vocab terms that we've had so far. Talking specifically about elements, we've got 118 of them on the periodic table thus far. I say thus far because we're continuing to find new ones, right? In our particle colliders that we've got either in Batavia, Illinois at Fermi or all the way over at CERN in Switzerland, we're constantly creating new elements. Will we be able to go beyond 118? That's a conversation for a different day. We'll get there eventually. I think we will. I don't know why we couldn't. I just don't think it's going to be very easy to pull off. But elements are always going to have, anytime we write out an element, how are we going to differentiate an element from a compound is ultimately where we're getting here. Elements are going to have a symbol, and all those symbols are on the periodic table in the back of the room directly behind you. Those elements are going to be written out in either a single letter or a capital letter and a lowercase letter. But a compound is going to have a formula. It's going to be many of these different elements all together, right? So we could have barium, which is just B, boron, which is just B, or barium, which is Ba, carbon, which is just C, or calcium, which is Ca, hydrogen, which is just H, or helium, which is He. And then we're all familiar with how we would write these out in formulas, right? If we've got hydrogen and oxygen, H and O are the symbols for the individual elements. When we write it out in a formula, we all know that's H2O. Or sugar is C6H12O6. We have carbon, hydrogen, and oxygen in the formula in a ratio of 6 to 12 to 6 or 1 to 2 to 1 if you want to reduce it, right? But that's how we differentiate the two. We're going to come back to these in a lot of detail later on. But this is the vocab that we need in order to start those conversations and be successful in them. So as is always, if you have questions, if you have concerns, don't hesitate to reach out on Teams chat and let me know what's going on. I'd be more than happy to help any of you guys out. I hope this helps, and I'll see you on the other side.